Okay, so you'll notice the outline is very complicated. That's because this used to be, I used to combine the rubber elasticity and this into the same lecture, and it ended up being like in the same note set. And I thought it was too much of a departure from one topic to the other, and that it fit more naturally with creep. So I pulled it out. All right, but for the most part, with this, when we're talking about viscoelastic materials, we're talking about either polymers or a lot of biomaterials exhibit viscoelastic effects, right? Basically, covalently bonded things where you have discrete units that end up being less firmly bonded to other discrete units, right? Exhibit viscoelasticity, right? And viscoelasticity is sort of it's got a very clearly defined term in some sense, or clearly defined. It's clearly defined in some senses, but in others, it's more nebulous, right? And so we say it basically falls somewhere between two other idealized cases, right? The elastic solid, which we spent a lot of time talking about, right? It forms by external loads, but reverts instantaneously to the original shape when the loads are removed. Or a pure viscous liquid, right? It flows irreversibly under the action of any shear force, right? It's a viscous liquid is unable to withstand any shear force without a permanent flow, right? So we have somewhere in between the two of these, right? So the classic example is silly putty, right? Everyone's played with this, or still does, right? If you leave it in the egg, it takes the shape of the egg, right? But if you bounce it, right, it acts as a pure, perfectly elastic rubber ball, right? So that means that the response of the material depends on the time scale at which the load is applied, right? An instantaneous load that doesn't give time for rearrangements, you act like a elastic solid. Slowly applied load, you act like a viscous liquid. Right? Polymer melts are interesting. Has anyone ever in undergrad classes had to take a course in polymer processing? Right? Like either extrusion, a screw extruder. Right? It's really interesting. The rate at which you flow a polymer melt through a die, it behaves either sort of like, you know how when you squeeze honey, it spirals out, right? You can get that, but then those instabilities become even more, and then it'll fracture, right? So you'll have melt fracture of a liquid, which is a very strange thing when you think about it. Okay, so if we have a purely viscous flow, you say the strain rate is some function, or the stress is some linear function of the strain rate, right? That's a linear viscous law, right? It's analogous to Hooke's law, except it relates stress to the deformation rate rather than the deformation, right? And so this is just the classic viscous law. If eta is independent of stress, remember we have Newtonian viscosity. If our viscosity does depend on the stress applied, then we have a non-Newtonian viscosity. Right? For viscoelastic, we're going to assume a superposition of the stresses, right? Where the stress is going to depend on the instantaneous strain by Hooke's law and on the instantaneous strain rate, right? Hooke's law tends to be the dominant term at small strains, and Newton's law for slow flow rates, right? So we have the same kind of idea, right? We had elastic strains tend to be small strains, right? The Newtonian flow tends to be at higher shear rates. And we're going to cover some nonlinear aspects of viscoelasticity where we have significant deviation from this kind of behavior when we talk about creep. So we have a time-dependent change at a constant stress. So we come here, we add a load, right? Zero stress, we add some load. Zero stress, we add some load. We get an instantaneous elastic response, right? That's the Hooke law part. Then we get a time-dependent viscous flow, right? Then when we unload, we recover our elastic part instantaneously. And then we have a time-dependent viscous recovery, which depending on how long we wait, there may be something that we call a permanent flow, non-recoverable flow, right? If it's an ideal viscoelastic material, there is no permanent plastic flow, right? If we have, or if we wait an infinitely long time and it recovers, right? Did anyone see Jay Sayers' talk? It was a sort of a special colloquium. He's the vice president of IMR. He gave a really nice talk about, you know, those barriers on the highways where, you know, you have a bridge abutment, and then you have the barricade that has these energy-absorbing car pillows in there so that you don't crash into the concrete. The design was very interesting because they were really concerned about the recovery of this, right? They wanted it to absorb a large amount of energy quickly, but also not have a permanent plastic set at the end of, right, when it was able to recover. So they needed this time to be very fast, and this plastic set to be very small, right? So what do we mean by linear viscoelastic, right? If that equation was linear, scaled all of our stress by a factor of 2, it means that our strains and our strain rates also scale by a factor of 2, right? It's a linear function, right? So that means our instantaneous, if we double our stress, our instantaneous elastic response doubles, right? Everything scales linearly in our time-dependent region. We still recover twice as much elastic strain instantaneously when we remove the load, and our recovery rate is twice as fast, right? And our plastic set is also twice as much, right? So the time stays exactly the same. The time from here to here is the same, but our recovery rate doubles, right? Right. All we're doing is essentially putting, you double this term doubles, and this term doubles. Okay, so I forgot to make one important point. So we're going to generally use the term creep. So creep, when we're talking about viscoelasticity, is a little different than when we talk about creep if a turbine blade in service temperatures, right? For this, we're going to consider creep to be the time-dependent change in strain given a constant stress, right? When people talk about creep testing, they talk about in-service components. They'll also talk about stress-controlled creep and strain-controlled creep tests. Here, we're really, when we say creep in the sense of viscoelasticity, we mean the time-dependent change in strain at a constant stress, and stress relaxation as the change in stress at a constant strain, right? Okay. So we can define a compliance, right? So if our material is linear, the magnitudes of our initial elastic strain, our time-dependent strain, and our permanent plastic strain are proportional to the magnitude of the compliance. So we can define, or proportional to the magnitude of the applied stress. So we can define this creep compliance, which is the ratio of the strain as a function of time over our stress, right? So the units of this are going to be Pascal inverse, right? Same as our elastic compliance. And we can basically just break this up into three distinct regions: our elastic, our time-dependent, and our plastic, permanent plastic set, right? And so we can then talk about different material classes with respect to each one of these effects. So if we have linear polymers that don't have a lot of branching or cross-linking, such as low-density polyethylene, right? We have a significant permanent plastic set here, right? So, right, at temperatures above the glass transition, this J3 term dominates. At low temperatures, J1 and J2 are important. In semi-crystalline polymers, this permanent plastic set tends to be very small, right? And heavily cross-linked polymers show no permanent Newtonian flow, right? To an approximation, right? You don't worry about your car tires getting a flat spot when you leave it in the parking lot for a day or two, right? But if you leave a car sitting for a year, right, without driving it, those tires are trash, right?
Can you very briefly go back over what E1, E2, E3 is?
Oh, yeah.
You're not talking about the directional, right?
No. Those are the notations, right?
Oh, okay, right. From
right. Yeah. So this is the elastic portion of the displacement, the time dependent, and the permanent set. Okay. So if we look here, since strain has a function of time, our compliance is a function of time, right? And so the amount, right? And so remember here that we're talking about this, we want the strain, right, is our stress times our compliance. Right? So we're applying stress. So basically this curve is all about how fast our stress is applied, right? So in this case, this here, this glassy regime, this is our elastic, viscoelastic, rubbery. Right, what do we mean rubbery? Right, this is that silly putty regime. Right? It's not, rubbery is not a very good word, right? Because when you think of rubbery, you think of, right, a pure elastomer. Sometimes other books call it leathery, which makes even less sense to me. Right? But really, this is kind of like the silly putty-like behavior. These are sort of old terms that were around before those. Cool toys were invented and then a plastic flow regime. Right? So the cool thing about this is we'll talk about this when we talk creep. We can use in the next lecture. We can use this to develop a sort of time temperature superposition. Right? We can look at how these viscosities change with temperature to relate how they're going to change with time. Right? So if we have a material that flows very, very slowly. Right? We can't sit around and wait for that to happen to measure our compliance, right? But we know the shape of the curve sort of in this region. Then we heat the material up, and we get a shift. But at that point, we can measure the whole curve. We can overlap the regions where our compliances match up to extend our range, and we'll talk about that more in the next lecture. The opposite of creep, or I say the complement to creep, is stress relaxation. Here we hold the material at a fixed strain, and we look at how the stress decays with time. Right? So again, here we apply a strain. We have an elastic response in stress, right? And then over time, that stress is going to decay when we have a constant. Right? Now, if it were to decay all the way to zero, and we were to let go of it, there's no driving force to bring the thing back, right? So it's just permanently deformed, right? And so we can define a relaxation modulus that's completely analogous to our creep compliance, right? It's going to have the units of pascals. It's a little easier to interpret for people because it matches elastic modulus intuitively a little better. So if you're in this glassy region, right, you have a very short time of your strain. Your stress is high because your modulus is high. But if you hold it for a long time, your stress decays. So now this is where things start to get fun. Philosophical. So Boltzmann, way back in 1876, was looking at this, and he said that creep can't really be determined by the instantaneous load. You need to know what the entire loading history of the part was in order to compute what's going on. Right? Each loading step makes an independent contribution to the final deformation. So that if we know all the history, we can just sum it up. Right? This is kind of like almost quantum-like view, right? Sum over histories. But anyway, right, and again, so this fits in this same kind of time frame that really critical contributions to thermodynamics were being made, right? And so it shouldn't be surprising that the same names kind of pop up, right? Basically what he's saying is that strain or stress is not a thermodynamic state theory, right? It's not, creep is not a path-independent process. But we talked about this with plasticity, that the end point, the final strain is not enough to determine the energy dissipated. Right? You need to know what the path was. The same thing here, right? But because we're making a linear approximation, all I need to do is take all the little individual loading events and add their effects together. Right? So if we have stresses that are added at these times, the creep at time t can just be added up as the linear contribution of these time-shifted events. Right? So we'll go through some examples where this will make a little bit to make this a little more sense, right? Usually this ends up being written in integral form, but we can just think of it in the discrete form for now, right? So the elastic strains are instantaneous, right? So we can pull these out and define this unrelaxed modulus, right? Right. So this here is the stress at the end of the experiment, right? We define this term as the unrelaxed modulus, and there's a completely analogous equation for relaxation. Working through the equation is not really important. What is important is this notion of the superposition principle. And just as a simple example, right? If we think of a two-step loading here, right? If we load, we get our instantaneous elastic response, and then a time-dependent elastic response. And we can just think of this as going on forever, right? So this just keeps going and going and going, and it gets asymptotically flatter, and eventually it will flatline out to zero, right? This curve here. And then we add another stress, right? We get our instantaneous response and the time-dependent curve, right? And this curve here is just a time-shifted version of this one. Right? All we're doing is taking this and sliding it over. And then our total response is just the sum of those two. So, right, follows this. Right? So that's basically Boltzmann in a nutshell. Right? You can take your individual loading events. Right? If this second curve were twice as high, this bit here would just be a time-shifted version scaled by a factor of 2. So we can think of the same thing when we have superposition for unloading. Here we add our instantaneous stress. We have a time to do this. We just pretend this goes on and on and on forever. Right? This just flat lines eventually because it's asymptotically decreasing. Right? Now the unloading we can think is the same as adding a negative. Right? We're going to add a negative load. So here we have this picture out of the book I don't like. Really, we should just flip this around the axis and show a negative strain here. And then like this. But this is the one in the reading, so I want to change it up. But you can think, so here we have a time-shifted version of this, but it's negative. Right? So the effect, again, is just the additive sum of the two curves. Right? So it comes up, boom, and the recovery, right? And notice because this curve here, the way it is, it asymptotically goes to flat. This curve here asymptotically goes to flat. So after a long enough time, the difference between these two is going to be very small, right? And we're going to have almost full recovery, virtually full recovery after a long period of time. But all we're doing is we have one curve, we just shift it and scale it, and add them all together. I don't understand why somehow I shut like Outlook completely, and it still gives me background notifications that only play when it's in full screen mode. Like those dings don't come up if I have the screen open. Okay. So this last bit here, this should be pretty much a review. You probably saw this going back to Callister for your introductory to material science. You probably have forgotten it all. Right, but basically, from Boltzmann, we know if we know the shape of this curve under a small test load, right, we can figure out the shape of the total curve from everything else, right? But what defines the shape of this small test load, of the stress response or the strain response under the small load? And for that, we have a couple different elementary models, right, to describe these different responses, right? So the Kelvin or Voigt, these are the classic spring dashpot models. Hopefully, start to ring a bell a little bit. Maybe you've seen this, right? The spring, you know, from simple physics, this is your classic ideal elastic element. Your dashpot is a viscous element, right? Think of this as being a piston that doesn't quite fit perfectly. So when you press it together, you get hydrostatic pressure here that pushes some viscous liquid past this piston slowly, right? So you have a time-dependent resistance, right? That's going to be proportional to the amount of stress, the amount of force that you push on it. Or the resistance is going to be dependent on how fast you're trying to push this thing and how fast you're making the fluid go past the sides of the system. That's the dashpot model. So if we think about what happens if we put a stress here, right? The dashpot is going to resist the instantaneous response of the spring, right? So we're basically unloading. We're going to have this time-dependent response controlled by the dashpot. When we unload, the spring provides the driving force for recovery, right? Because now we're storing energy in the spring. When we let go, the spring is slowly going to pull the dashpot back into its alignment. Anyone, right? Motorcycle or race car, right? People who do go-kart racing, right? This is a steer damper. Okay. And so the Kelvin or Voigt model, they're in parallel. Okay.
It's a Monday.
It's a Monday in every sense of the word. Okay. So then, if we put them in series, this is the Maxwell, right, unit. And so here you can see, if we put a stress on it, we get an instantaneous response out of the spring, right? Then a time-dependent flow of the dashpot, and then when we let go, the spring instantaneously recovers, but there is no driving force to pull the dashpot back now. So now we have a permanent plastic set, right? And then, so the limitation of the Voigt or Kelvin is that we don't have an instantaneous elastic response. The limitation of the Maxwell model is that we don't have a time-dependent recovery. So if we combine them together, right, and basically we add another spring here, right? We have our spring. We put a This is a Maxwell model in parallel with the spring, right? Now, you see, we would get an instantaneous stretch, right? We get something that looks very much, where is, there. We get something that looks very much like this, right? The first spring stretches, then we have the second, the dash pot stretching. When we unload the parallel spring, we'll slowly pull the dash pot back, right? This is the parallel spring, the parallel spring unloading. Right? So the nice thing about these Voigt and Maxwell models is they're linear first-order differential equations, which means you can solve them analytically. Everyone should be able to. So you'll have to you'll do a very quick refresh on solving differential equations by integrating both sides. Right. Again, it's not hard. Right? So you end up with a differential equation that looks like this. This viscosity divided by the modulus, Young's modulus, here, that you end up here when you work through. This is a representative relaxation time, right? It's the rate at which is the critical deformation rate. Critical deformation rate for the system, right? And it's all nicely solved in terms of the modulus of the spring, stress, and the deformation, right? And that allows us to explicitly solve for our compliance, right? And you get to work through this a little bit more detail for the homework. But if we look at the setup, right? So we're in parallel here, right? So again, we just have our stress as a function of our elastic contribution plus our viscous contribution, right? And we work it out from there. Right? Maxwell model, right? We have a spring and dash pot in parallel. If we remember our electrostatics, or electric circuits, right? If we have a resistance RC circuit in parallel versus an RC circuit in series. Right? So we have a differential equation that looks like this. Right? And again, we can solve for stress. And basically, we say that under constant stress, we only have a Newtonian flow. We don't have stress relaxation. For the standard linear model, we add that second spring. We get a more physical response. Both springs in the system are extending. Right? So we have to change how we define our relaxation time. It's not just viscosity divided by the modulus. We have the contribution of the two springs in series. Right? And so we can work through the equation and solve for a stress response that looks like this. Again, solving the differential equations is not important to me, right? But just sort of understanding the basic physical picture of these three models, right, is the key thing. Right? If we think about what the big ideas that we looked at with viscoelasticity is Boltzmann, right? We just can sum up all of our loads, right? If we know the response to our system to some test load, right? We then know it for any arbitrary loading condition that we can put on it, and that we can use some of these very simple models if we know some basic things about our system to define what to model what the test response is, right? And then basically understanding how the structure of the material is going to, which is going to be most representative, right? So if we look at these three systems, right? A system that is a polymer system that is non-crystalline, relatively low molecular weight without any significant cross-linking, right? Those little butter tubs, LDPE, right? Yogurt containers, right? We're going to have a response that looks something like this, right? What's the restoring force in our system? The chains slide past each other. Right? You're not going to pull it back, right? This could also be used to model, say, silly putty at very, very long times, right? You put it in the egg and let it sit for a week and you come back. It's the shape of the egg. Right? So relating these simple models to what's going on in the material and the time scales, right, are also things that I want you to think about. I can guarantee you that I am not going to ask you to solve any of these equations on the exam. Differential equations on the exam, right? And the questions to ponder, sure, right? We'll play with it, just because it's worthwhile going through them all once, right? But please don't memorize them or think you're going to have to be required to solve them. Right? So I'm going to throw these last couple slides on DMA in, and then I want to work through a problem. Mostly because we don't actually have any DMA equipment, dynamic mechanical analysis equipment. In the department, no one does these measurements. So how do you actually measure the viscoelasticity in a material? How do you determine whether something is exhibiting a significant viscoelastic behavior, whether it's just a time-dependent flow thing, right? And more importantly, if it is exhibiting viscoelasticity, how do you determine whether it's linear or not? Right. So basically, this is a tester where you subject the strain control to a cyclic strain, and you measure the stress, right? Okay, and then think about in an electric system, an AC electric system, what's the phase lag, right? Ideally, current and voltage are 90 degrees out of phase, right? Here, we're talking about mechanical lag. We're looking at this phase shift between the applied strain and the stress, right? So obviously on the first cycle, right, if there's an elastic component, right, that's going to come up, right? You keep cycling it, right? And eventually it reaches an equilibrium. right, where you're driving this and you're measuring the stress. And they will both vary sinusoidally, but you'll have a lag, right? And the stress can be decomposed into two components. One that's in phase with the strain, and the other that's 90 degrees out of phase with the strain. Right? And this gives you you can use this to define what we call a complex modulus. Right? Very similar to impedance. The MSE circuit has a lot of parallels. Right, so this G1 here, this is the storage modulus, right? And this is the amount of defines the amount of elastic energy that's stored in the sample due to the applied strain. G2 is the loss modulus, and it's the 90 degrees out, and this is the energy dissipation, right? And so we can quantify the viscoelasticity in our system by looking at how much energy we're storing, how much recoverable strain energy we're storing versus how much we're dissipating through viscous flow, right? So this is the elastic portion. This is the viscous flow portion, right? And so our phase shift is pretty small, right? Tan theta is about 1%, right? And so we can look at how the complex modulus varies as a function of our frequency for most polymers. Obviously, at very high frequencies, right, there isn't time for any viscous flow, right? And so everything is perfectly glassy. Our loss modulus is basically 0. As we come down, our storage modulus decreases, and at very low frequencies reaches a minima, right? And then our loss modulus, right? So we have this region in the middle from the contribution of the two. This is the tangent of our phase shift, right? And we can basically define a viscoelastic region where this phase shift is at some kind of peak. So for fun, I actually got Jay Sayer was nice enough to send me all of the DMA data that they collected for this highway overpass project, right? And so as part of the project problems, we did a simple analysis of computing the storage and loss modulus and the creep compliance of that material from the